What if Earth's deepest past is not as empty as we think? Across millions of years, cities can vanish, monuments can crumble, and every visible trace of civilization can disappear. But stranger clues may survive in rocks, ice, oceans, climate shifts, and even DNA. This story examines the possibility that human civilization may not be the first advanced society to exist on Earth. Today, we explore one unsettling question. Could another civilization have existed here long before us now? Let's begin. A NASA scientist sat down one afternoon and asked a question that nobody in mainstream science wanted to touch. Not because it was absurd, but because the answer was genuinely terrifying. The question was this: if an industrial civilization had existed on Earth 60 million years ago, not aliens, not mythology, just another species that built cities and burned fuel and split atoms, would we be able to find a single trace of it today? He ran the numbers. He consulted the geology, and his answer was no. Almost certainly not. That scientist was Gavin Schmidt, director of NASA's Goddard Institute for Space Studies. In 2018, he co-authored a paper with Adam Frank, astrophysicist at the University of Rochester, published in the International Journal of Astrobiology. The paper had a name that sounded like science fiction, but read like a sober, footnoted academic argument: the Silurian hypothesis, named after a classic Doctor Who episode featuring a reptilian civilization that predated humanity. But make no mistake, what Schmidt and Frank proposed was not fiction. It was a genuine scientific framework, a real question, asked with real methodology, by real researchers with institutional credentials. The question they were actually asking was not, did ancient civilizations exist? The question was sharper and more destabilizing than that: would we even know if they had? To understand why the answer is probably not, you need to understand what geological time actually does to physical things. The surface of Earth is not a static museum. It is a conveyor belt. Tectonic plates grind and subduct, pulling ocean floor down into the mantle at a rate of a few centimeters per year, which adds up over millions of years to entire ocean basins being recycled completely. Rain and wind erode mountains down to flat plains. River systems carry sediment to coasts, burying older layers under newer ones. The ground you stand on is constantly being destroyed and rebuilt from scratch. Reinforced concrete, the material we use to build skyscrapers, highways, and bridges, has a structural lifespan of somewhere between 100 and 500 years before it begins to degrade without maintenance. Without anyone to repair it, a modern concrete structure in a wet climate crumbles significantly within a few thousand years, gone entirely within tens of thousands. At the scale of millions of years, concrete does not leave a layer in the rock record. It leaves essentially nothing detectable. Steel corrodes, glass devitrifies, plastics fragment. Even the largest structures humans have ever built would be geologically invisible within a few million years of abandonment. Now scale that up. Think about New York City. 8 million people, thousands of skyscrapers, hundreds of miles of subway tunnels, bridges, power grids, an entire civilization's worth of infrastructure, compressed into a few hundred square miles of island and coastline. After 50 million years of geological processes, New York City would leave behind a sedimentary layer thinner than a sheet of A4 paper, thinner than paper. That is not a metaphor chosen for dramatic effect. Schmidt and Frank calculated this explicitly in their paper. The chemical and physical traces of a civilization operating at our level of industrial output, compressed into the rock record after 50 million years of erosion, subduction, and metamorphism, would be functionally indistinguishable from natural geological variation unless you knew exactly what chemical signatures to look for. And you were looking in exactly the right place. Most of the ocean floor that existed 60 million years ago no longer exists. It has been pulled under tectonic plates and melted back into the mantle. The continents themselves have shifted. Coastlines that once held cities are now hundreds of miles inland, or underwater, or buried under kilometers of sediment. What do you think is the single thing our civilization will leave behind that lasts the longest? The pyramids of Giza, too soluble over tens of millions of years limestone dissolves. The Hoover Dam structurally unrecognizable within a few million years of no maintenance. Satellites in orbit. They decay, re-enter the atmosphere, and burn up within centuries to millennia. The internet entirely dependent on active infrastructure. Pull the power, and it is gone within decades. Take a moment. Think about it genuinely. The honest answer, and this is one of the more ironic findings in the scientific literature, is that the most durable legacy of human industrial civilization may turn out to be the plastic shopping bag. Not because the bag itself survives intact, it does not, but because the molecular fragments of synthetic polymers, broken down into microplastics and nanoplastics, embed themselves into ocean floor sediments under chemically stable, anaerobic conditions and may persist there in detectable concentrations for tens of millions of years. We have erected monuments to ourselves in stone and steel across 6,000 years of recorded civilization. And the thing that outlasts all of it might be the bag from a Tuesday afternoon grocery run. Gavin Schmidt did not intend this as comedy. But the universe occasionally writes its own punchlines. This brings us to the core of what the Silurian hypothesis actually argues, and why it matters far more than any fringe archaeology claim or ancient astronaut theory ever could. The absence of evidence is not evidence of absence. These are not the same statement. In everyday life, we treat them as equivalent. Check your pocket. No keys are not in your pocket. Reasonable. But geology is not your pocket. Geology is a system that actively destroys information over time, systematically and without exception. When you search the geological record and find nothing, that absence tells you far less than you instinctively assume. Schmidt and Frank built a formal scientific framework around this distinction. They asked, what is the actual detection threshold of the geological record? How advanced would a civilization need to be? How long would it need to operate? And what specific signatures would it need to produce in order for us to find its fingerprints in rocks that are tens of millions of years old? Their conclusion, a civilization that burned fossil fuels at roughly our current scale for a few thousand years, would leave detectable isotopic anomalies in carbon ratios and certain rare metals. A civilization that produced industrial polymers would leave microplastic traces in deep ocean sediments. A civilization that used nuclear technology would leave specific isotopic signatures locked into the geological layers of its era. Not buildings, not bones, not monuments, chemistry. That is what survives. That is the only language deep time allows. We cannot prove a prior civilization existed. Schmidt and Frank never claimed otherwise. But what they demonstrated, rigorously, in a peer-reviewed journal, is that we also cannot rule it out, not with the geological tools we currently have, not for civilizations that operated more than a few tens of millions of years ago. The rock record has a detection threshold. Civilizations operating below a certain duration or above a certain geological age vanish without recoverable trace. That is a very different intellectual position than where science stood before 2018. And it changes every question that follows. But if we cannot find direct ruins, there is something else that geology cannot erase. Something that does not need stone or steel to survive. It is written directly into the rock itself. And what it says will genuinely unsettle you. 541 million years ago, something happened in the oceans of early Earth that biologists have spent over a century trying to explain and still cannot. Not fully, not in a way that satisfies the data. In less than 20 million years, which, on the 4.5 billion year timeline of Earth's history is the geological equivalent of blinking more than 30 distinct animal phyla appeared simultaneously in the fossil record, not gradually, not as a slow accumulation of transitional forms spread across hundreds of millions of years of patient Darwinian process. All at once, complex, differentiated, fully formed body plans with eyes and limbs and nervous systems and digestive tracts materializing in the oceans as if someone had loaded a program and pressed execute. This is the Cambrian explosion, and it remains one of the most contested, most uncomfortable events in the history of life on this planet. The reason it is contested is straightforward. It should not have happened that fast. Darwinian evolution natural selection, acting on random genetic mutation, is powerful, but it is slow by necessity. The development of a fundamentally new body plan, a new phylum-level architectural solution for life, requires the accumulation of hundreds of thousands to millions of individually beneficial mutations across enormous numbers of generations. The fossil record before the Cambrian is populated almost entirely by single-celled organisms and simple multicellular forms: sponges, algae, thin films of microbial life clinging to seafloor rocks. Then, in 20 million years, you get eyes, bilateral symmetry, active predation, jointed limbs, centralized nervous systems, the foundational blueprints for nearly every animal group alive on Earth today. Standard evolutionary models predict this process should require hundreds of millions of years minimum. 20 million years is not a compression. It is a violation of the expected rate by an order of magnitude. Something does not add up. The physical evidence comes from two sites that have preserved Cambrian fauna in extraordinary detail, both now recognized as UNESCO World Heritage locations, which gives some indication of how scientifically significant they are. The Burgess Shale, discovered in British Columbia, Canada, in 1909 by Charles Walcott of the Smithsonian Institution, contains thousands of specimens of soft-bodied Cambrian organisms preserved with exceptional resolution. Creatures like Anomalocaris, a predator roughly 1 meter in length, equipped with compound eyes and articulated grasping appendages, appears in the Burgess Shale fully formed, with no transitional ancestors in the sedimentary layer immediately below. Hallucigenia, another Burgess organism, is so structurally unusual that paleontologists initially reconstructed it upside down, genuinely unable to determine which end was the head. The Chengjiang fossil site in Yunnan Province, China, discovered in 1984, adds thousands more species to the picture, many representing phyla with no identifiable evolutionary precursors anywhere in the Precambrian record. These organisms do not have visible ancestors. They appear complete, functional, immediately radiating into ecological niches as though the ecological framework had been designed in advance and was simply waiting to be populated. No half-built eyes, no proto-nervous systems caught mid-development, no intermediate forms bridging the gap between what came before and what suddenly appeared, just finished products, showing up at the same moment across multiple continents separated by vast ocean distances. The scientific community has not ignored this problem. Several triggers for the Cambrian explosion have been proposed and seriously investigated. Rising atmospheric oxygen in the late Precambrian, making complex aerobic metabolism energetically possible for the first time. A series of severe snowball Earth glaciation events followed by rapid environmental destabilization, generating intense selection pressure. Changes in ocean chemistry affecting the availability of calcium carbonate, suddenly making mineralized hard parts shells, exoskeletons biologically achievable. Ecological feedback loops where the first predators drove rapid evolutionary arms races. Each of these mechanisms is real. Each contributes something genuine to the explanation. None of them, individually or in combination, fully accounts for the speed. More oxygen explains why complex life became chemically possible. It does not explain why more than 30 phylum-level design solutions all became actual within the same geological window. Predation pressure can accelerate evolutionary change, but not by the orders of magnitude required to compress hundreds of millions of years of expected process into 20 million. There is no scientific consensus on what produced the rate we observe in the rock record. As paleontologist Simon Conway Morris of Cambridge University has written, "The Cambrian explosion remains, in his words, one of the most profound mysteries in the history of animal life." That is not a fringe position. That is a Cambridge professor summarizing where the field actually stands. Does any of this feel familiar to you? Something wipes the slate clean, and then a newer version shows up faster than before. Think about your own devices. Every few years, a generation of technology is phased out, not because it completely failed, but because something with entirely new architecture is ready to replace it. And the new version does not gradually become itself. It launches, suddenly present, with capabilities the previous generation never had, with no visible intermediate prototype in the consumer market. The Cambrian explosion follows the same structure. The Precambrian is the old generation. Then something clears the space, and the new architecture launches complete, capable, immediately functional with no prototype visible in the layer below. What makes this genuinely difficult to dismiss is that the Cambrian explosion is not an isolated event. The same pattern repeats throughout Earth's biological history with a regularity that strains coincidence. End Ordovician extinction. 443 million years ago, roughly 85% of species lost. What follows is rapid diversification of fish and early terrestrial plants. End Devonian. 372 million years ago, 75% of species eliminated. What follows is the rise of tetrapods, four-limbed vertebrates that eventually become reptiles, mammals, and humans. End Permian. 252 million years ago, the worst extinction event in Earth's history. 96% of marine species and 70% of terrestrial species gone. What follows is the rapid rise of the dinosaurs. End Cretaceous. 66 million years ago, the dinosaurs disappear within a geological instant. What follows is the explosive radiation of mammals and eventually, us. Each time, the pattern is identical. Mass extinction, rapid vacuum, accelerated emergence of organisms that are measurably more neurologically complex than the ones that preceded them. Each reset produces life with larger brains, more sophisticated nervous systems, greater behavioral flexibility than the version before. If you graphed the average neural complexity of dominant life forms across 500 million years, the line would not trend smoothly upward. It would be flat, then spike, then flat again, then spike again. Always immediately after an extinction event, not gradually ascending, jumping, like a system being updated in discrete versions rather than continuously improved. Sounds like someone is running Earth like a strategy game and hitting New Game Plus every time the server crashes. The saves don't carry over, but whoever is running the game clearly remembers what worked last time because each new version launches more capable than the one it replaced. Now, to be precise, the standard scientific explanations for the Cambrian explosion are not wrong. Oxygen levels, environmental triggers, ecological opportunity. These are legitimate contributing factors supported by real data. The argument here is not that those mechanisms did not operate. It is that they do not fully close the gap between what evolutionary theory predicts and what the fossil record actually shows. That gap is real. It is acknowledged in peer-reviewed literature. And it sits there, unresolved, at the most important transition point in the history of complex life on this planet. 30 phyla, 20 million years, no visible ancestors. Something accelerated the process. Whether that something was an undiscovered natural mechanism, an environmental trigger we have not yet fully characterized, or something else entirely the rock record does not yet say. But if something intervened in the biology of this planet, it left a fingerprint, and that fingerprint is not preserved in bone or shell. It is locked into the chemistry of the rock itself. What the chemistry shows next will change the entire frame of this conversation. In 2021, a team of scientists analyzing 56-million-year-old sediment cores pulled from the ocean floor found something that stopped them cold. The cores came from the geological boundary of an event called the Paleocene-Eocene Thermal Maximum, the PETM, a period when Earth's temperature surged between 5 and 8 degrees Celsius over approximately 20,000 years, and atmospheric carbon dioxide spiked so dramatically that ocean chemistry shifted globally. It is the most rapid and severe natural warming event in the last 66 million years of Earth's history, and for decades, geologists assumed it was caused by some combination of volcanic outgassing, methane release from seafloor sediments, or orbital forcing. What the 2021 analysis found in those cores was a carbon isotope anomaly specifically, an unusual shift in the ratio of carbon-13 to carbon-12 that was, in the words of the researchers, nearly identical in structure and magnitude to the isotopic signature produced by modern industrial fossil fuel combustion. Not similar, nearly identical. To understand why that is extraordinary, you need to understand what carbon isotopes actually record. Carbon comes in two stable forms. Carbon-12 is the common version, lighter, faster, preferred by living organisms during photosynthesis and biological processes. Carbon-13 is the heavier, rarer version, less favored by biology, more prevalent in inorganic geological materials. When you burn fossil fuels, coal, oil, natural gas, you are burning the compressed remains of ancient organisms, all of which were rich in carbon-12. That combustion floods the atmosphere with a disproportionate surge of carbon-12, driving the carbon-13 to carbon-12 ratio sharply downward. Think of it like a cocktail. The natural atmosphere maintains a certain ratio of the two, a baseline recipe. Every time industrial civilization burns fossil fuels, it pours an enormous extra shot of carbon-12 into the glass, throwing the ratio measurably off balance. That imbalance is chemically preserved in whatever sediment or ice or rock forms during that period. It becomes a timestamp, a signature, a fingerprint of industrial-scale combustion, locked into geological layers. That fingerprint has a specific shape, a specific rate of change, a specific magnitude. The PETM anomaly matches that shape. The PETM is not a minor footnote in Earth's climate history. Global temperature rose between 5 and 8 degrees Celsius. That is an enormous shift. The difference between our current climate and full glacial conditions is only about 5 degrees in the other direction. Sea surface temperatures in the Arctic reached roughly 23 degrees Celsius. Tropical ocean temperatures may have exceeded 35 degrees Celsius in some regions, approaching the thermal tolerance limits of complex marine life. The carbon-13 to carbon-12 ratio dropped sharply, rapidly, and in a pattern that the IPCC and multiple studies published in Nature through 2022 acknowledge remains not fully explained by any single proposed natural mechanism. Volcanic activity, methane hydrate destabilization, extraterrestrial impact, each has been proposed. Each has problems. None closes the gap completely. What would close the gap, isotopically speaking, is exactly what Schmidt and Frank identified in their 2018 paper, A Technosignature. Schmidt and Frank used that term deliberately. A technosignature is the chemical or physical imprint left in geological layers by the operation of a technologically advanced civilization the same class of signal that astronomers now search for in the spectra of exoplanet atmospheres when looking for signs of intelligent life elsewhere in the universe. Industrial combustion of fossil fuels, at the scale of a modern civilization operating for even a few thousand years, produces an isotopic anomaly in carbon ratios that is theoretically detectable in sediment cores for tens of millions of years afterward. The PETM carbon anomaly is the right type, the right shape, the right approximate magnitude. The anomaly occurs at the right geological moment for a pre-human industrial civilization to have operated and then vanished, with its chemical exhaust preserved in ocean sediment, while its physical infrastructure was erased by 56 million years of geological process. This does not prove a prior civilization caused the PETM. Schmidt and Frank did not claim it does. What they argued, and what the 2021 isotopic data reinforces, is that if such a civilization had existed, the PETM layer is precisely where its technosignature would appear, and we would not necessarily be able to distinguish it from a natural event using current methods. That is not a conclusion. That is a problem, a real one, an open one. The iridium anomaly at the Cretaceous-Paleogene boundary adds a second layer to this. 66 million years ago, at the precise geological moment when the dinosaurs disappeared, a thin layer of iridium, a platinum group metal vanishingly rare in Earth's crust, but relatively common in certain types of asteroids, appears globally in the rock record. This was the discovery that led Luis Alvarez and his colleagues to the asteroid impact hypothesis in 1980, a conclusion now broadly accepted as the primary driver of the end Cretaceous extinction. But the iridium distribution across that boundary layer is not uniform. Multiple studies have documented sites where the concentration, the isotopic composition, and the spatial distribution of iridium deviates from what a single large impactor would be expected to produce. Some boundary sites show iridium profiles that are spread across a thicker stratigraphic interval than a single instantaneous impact would deposit. Some show chemical associations with other platinum group elements in ratios that differ from the Chicxulub impactor's expected composition. The mainstream explanation involves secondary dispersal mechanisms, complex atmospheric and oceanic transport, and the possibility of concurrent volcanic activity from the Deccan Traps. These are legitimate scientific proposals, but the anomalous distribution pattern has not been fully resolved, and it sits alongside the PETM carbon signature as another data point in the geological record that is real, documented, and not entirely explained. If you wanted to leave a message for someone 60 million years from now, where would you write it? Not on stone, not on metal, not in any physical structure. All of that would be gone. The only medium that survives geological time is chemistry, specifically, the isotopic composition of sedimentary rock layers. That is the one archive that geological processes preserve rather than erase, because it is baked into the mineral structure of the rock itself, not written on its surface, which leads to a thought that is either darkly funny or genuinely alarming, depending on how you look at it. It turns out the most effective way to write a letter to a civilization 60 million years in the future is not to carve it in granite or seal it in titanium vaults. It is to pump enough chemically distinctive carbon into the atmosphere that the isotopic shift gets locked permanently into the sediment record of every ocean on the planet, which means we are, right now, writing that letter. Every coal plant running today, every barrel of oil combusted, every natural gas flare, we are authoring a carbon isotope anomaly that will be readable in ocean sediment cores 60 million years from now. Future geologists, if they exist, will look at that layer and see a sharp, rapid, industrially shaped spike in carbon-12. They will argue about what caused it. Some of them will propose natural mechanisms, and a few of them will publish papers suggesting that something burned fossil fuels at industrial scale, briefly, and then went silent. Congratulations! We are writing very diligently. The chemical fingerprint is only the first layer. The next thing locked inside ancient rock is something that, by every principle of natural chemistry, should not be able to form on its own ever. In 2020, a study published in Science Advances confirmed something researchers had suspected, but hoped was not true. Microplastics had penetrated every single deep ocean sediment core that had ever been drilled, every one, without exception, including cores extracted from depths corresponding to sediment laid down tens of thousands of years ago, long before the first synthetic polymer was ever produced in a laboratory. The contamination question in those cases is real and actively debated, whether the microplastics found in deeper layers migrated downward through bioturbation, through drilling contamination, or whether they genuinely represent primary deposition in those layers. The scientific community is working through the methodology carefully, but the finding opened a door that cannot easily be closed, because it raised a question that the field of geology had never seriously needed to ask before. What exactly is a synthetic polymer at the molecular level? And why does its presence in a geological layer mean something categorically different from any other unusual organic compound? Natural organic chemistry is extraordinarily rich. Life produces thousands of complex carbon-based molecules, proteins, lipids, carbohydrates, nucleic acids, pigments, toxins. The geological record is full of organic compounds produced by biological processes over billions of years. Finding unusual organic chemistry in an ancient sediment layer is, by itself, not remarkable. Synthetic polymers are different in a fundamental way. The molecular architecture of plastics, polyethylene, polypropylene, polyethylene terephthalate, polystyrene, requires reaction conditions and chemical precursors that do not occur in natural environments. Specifically, they require controlled high-temperature, high-pressure catalytic processes involving petroleum-derived monomers that nature does not assemble spontaneously. The long, repeating chain structures of synthetic polymers and the specific branching patterns of their molecular architecture are not produced by any biological or geochemical process known to science. In plain terms, if you find a synthetic polymer in a rock layer, something industrial put it there. There is no natural pathway to its formation. It is, by definition, a technosignature, the chemical signature of a manufacturing process that requires deliberate engineering. Under the right conditions, those signatures can survive for an extremely long time. Modern plastics fragment into microplastics under UV exposure and mechanical stress. But the fundamental polymer chain does not fully mineralize quickly. In anaerobic conditions, the low oxygen to low microbial activity environment found in deep ocean sediment columns, far below the seafloor surface, organic molecules can be preserved for millions to tens of millions of years. This is, in fact, the same preservation mechanism responsible for the formation of petroleum itself, ancient organic material buried under anaerobic conditions, compressed over geological time. The International Ocean Discovery Program, which operates the research vessel JOIDES Resolution and continues the work of the earlier deep sea drilling project, an ocean drilling program, has recovered sediment cores from every major ocean basin, some extending back tens of millions of years. Analyses of the organic chemistry in these cores have periodically flagged what researchers describe as anomalous organic compounds in layers where they would not be expected. Compounds that do not match the biological or geochemical context of their depositional environment. These findings are documented in the technical literature, typically attributed to contamination during core recovery, to migrating fluids carrying compounds from younger layers downward, or to incompletely understood natural organic chemistry. These are scientifically responsible default explanations, Contamination is a real problem in deep core analysis. Migration of organic compounds through sediment columns does occur, but the default explanation requires scrutiny every time it is invoked, because contamination and migration cannot always fully account for the chemistry observed, and the alternative that the compound was deposited when the layer was formed is not always ruled out. It is simply assumed to be impossible because the compound should not exist at that age. The assumption of impossibility is precisely what the Silurian hypothesis framework challenges. Think about what the geological record would look like if a civilization had produced synthetic polymers 50 million years ago, at industrial scale, for a few thousand years, and then vanished. Their plastic waste would have entered the ocean. It would have fragmented into microplastics. A fraction of those microplastics would have settled into deep-sea sediment under anaerobic conditions, below the zone of bioturbation, below the reach of most degradation processes. Over 50 million years, the polymer chains would partially degrade, partially transform, partially mineralize, but some fraction of the distinctive molecular architecture would remain detectable, embedded in rock that formed during their civilization's operational period. And we might have drilled through it already, in cores extracted by the deep-sea drilling project decades ago, analyzed with instruments far less sensitive than what is available today, and archived in core repositories where they sit, mostly unexamined, waiting. The Ocean Drilling Program Core Archive at Texas A&M University alone contains thousands of meters of sediment core from every ocean basin. A systematic reanalysis of archived cores using modern polymer detection techniques, the kind now used to find nanoplastics in human blood and lung tissue, has never been conducted specifically to look for anomalous synthetic organic signatures at pre-human geological depths. It has never been done. Not because the question is unscientific, because until very recently, no one thought to ask it. What do you think is the single thing from the modern world most likely to survive in the geological record, to still be detectable, in some form, millions of years from now? Not our cities, not our roads, not our art or our literature or our communications infrastructure. As established in Part 1, all of that is geologically ephemeral. The honest answer, the one that the microplastics data points toward, is synthetic polymer fragments specifically, the chemically distinctive molecular residue of industrial plastic production, preserved in anaerobic deep-sea sediment, which means the most enduring monument to human civilization on this planet may not be the Apollo landing sites on the moon, or the Voyager probes drifting through interstellar space. It may be the molecular ghost of a plastic drinking straw from a fast food chain, compressed into deep ocean mud, readable by instruments that do not yet exist, by scientists living in a world we cannot imagine. There is something both absurd and clarifying about that. Plastic is chemistry, but there is another category of trace entirely not chemistry, not molecular structure, but nuclear physics. And unlike organic compounds, isotopic ratios from nuclear processes cannot be faked, cannot be contaminated into existence, and cannot be explained away. What they record is absolute. In 1972, a routine quality control analysis at a uranium processing facility in France produced a result that made no sense. A shipment of uranium ore had arrived from the Oklo mine in Gabon, West Africa. Standard procedure required measuring the ratio of uranium-235 to uranium-238 in the raw material, a ratio that, across every uranium deposit ever analyzed anywhere on Earth, holds at a remarkably consistent value of 0.72% uranium-235. It is one of the most stable and predictable measurements in nuclear physics. Uranium deposited billions of years ago. Uranium found in meteorites. Uranium from mines on opposite ends of the planet. All of it reads the same. The Oklo sample read lower. Significantly, measurably, unmistakably lower. The uranium-235 had been partially consumed. Something had already run a fission reaction on it. French scientists dispatched to Gabon found not one anomalous zone, but 16 separate locations within the Oklo uranium deposit, where the isotopic ratios confirmed the same conclusion self-sustaining nuclear fission chain reactions had occurred naturally. Inside the rock, approximately 1.7 billion years ago, and had run continuously for roughly 150,000 years before the geometry of the ore body shifted enough to shut them down. The International Atomic Energy Agency investigated, confirmed, and published. The scientific community accepted it. Oklo is now the only known example of a natural nuclear fission reactor on Earth, a geological fact, fully documented, not disputed by anyone. Nature had built a working nuclear reactor, without engineers, without enrichment facilities, without control rods or cooling systems, just uranium, water, and the right geometry. And the physics ran itself, which immediately raises a question that sounds simple, but has no clean answer. If nature can produce a nuclear fission reaction that runs for 150,000 years and leaves a specific, measurable isotopic signature in the surrounding rock, then what exactly would an artificial nuclear event look like in the geological record? And more critically, would we be able to tell the difference? The answer depends entirely on which isotopes you are measuring and over what timescale. Plutonium-239 does not exist in nature in any meaningful quantity. Its half-life is 24,100 years, long enough to persist for hundreds of thousands of years after production, but short enough that any plutonium-239 present at Earth's formation 4.5 billion years ago has decayed to unmeasurable levels many times over. The only way plutonium-239 appears in the geological record is if it was produced recently in cosmic terms by neutron bombardment of uranium-238 inside a nuclear reactor or a nuclear weapon. Cesium-137 has a half-life of 30 years. It does not occur naturally at all. It is a pure fission product, created exclusively inside nuclear reactors and nuclear detonations, and nowhere else in the universe. Find cesium-137 in a sediment core, and you have found evidence of a nuclear reaction. The question is only when and where. These two isotopes are, in the precise technical language that Schmidt and Frank used in their 2018 paper, unambiguous technosignatures. They are isotopic anomalies that can't be produced by natural geological or astrophysical processes at Earth's surface. Their presence in a geological layer is a direct record of nuclear technology in operation during the period when that layer was deposited. A civilization that built nuclear reactors, or tested nuclear weapons, or experienced nuclear accidents at a scale comparable to what humanity has done since 1945, would leave plutonium-239 and fission product signatures in the sediment record of that era. Those signatures, depending on the burial conditions, could remain detectable in geological layers for hundreds of thousands to several million years, well within the detection window that careful isotopic analysis of sediment cores can reach. Schmidt and Frank identified this explicitly. This is not extrapolation. It is a direct prediction from known nuclear physics applied to the geological preservation question they were formally investigating. Now consider what has actually been found in the polar ice cores. The Greenland and Antarctic ice core records, particularly data from the GISP2 core in Greenland and the Epica core in Antarctica, contain detailed chemical profiles of the atmosphere stretching back 800,000 years in the Antarctic case and over 100,000 years in the Greenland record. These cores capture, layer by layer, the chemical composition of the atmosphere. At the time each layer of snow was compressed into ice. They are the most precise climate and atmospheric archive available to science. Within these records, Researchers have documented episodic spikes in certain radiogenic isotopes and beryllium-10, a cosmogenic nuclide produced when high-energy cosmic rays strike the atmosphere at multiple points that predate the modern nuclear era. Some of these spikes are well explained by known solar events, geomagnetic excursions, and supernova activity. Others remain subjects of active investigation, with proposed natural mechanisms that do not fully account for the magnitude or the chemical context of the anomaly. The records do not contain plutonium-239 at depths corresponding to pre-nuclear eras that has not been reported, but the broader pattern of radiogenic anomalies at unexpected depths, documented in peer-reviewed glaciological literature and acknowledged as not fully resolved, sits in the same category as the PETM carbon anomaly and the Cambrian fossil gap's real data, real uncertainty, real absence of complete explanation. If you were the scientist who pulled a sediment core from the ocean floor, ran the isotopic analysis, and found plutonium-239 in a layer 10 million years old, what would you write in your report? Sit with that question for a moment, genuinely. You would know what plutonium-239 means. You took the same nuclear physics courses as everyone else. You know there is no natural production pathway for it in that geological context. You know what you are looking at, and then you would look at your career, your institution, the grant committee that funded the expedition, the peer reviewers who will read the manuscript, the journalists who will call the moment the paper goes public. The most honest answer, and this is not a criticism of scientists, it is an observation about how human institutions process paradigm-threatening information, is that the first draft of the report would read instrumentation error, or contamination during core recovery, or anomalous result requiring further investigation before interpretation. Not because the scientist is dishonest, but because no one wants to be the person who dismantles the entire accepted framework of Earth's history on a Wednesday afternoon, in a finding that will immediately be called extraordinary and therefore requiring extraordinary verification that takes years to obtain. The Oklo reactor sat undiscovered for 1.7 billion years. When it was finally found, the scientific community needed months of investigation before accepting the conclusion, even though the isotopic evidence was straightforward and unambiguous. The bar for accepting that nature built a reactor was high. The bar for accepting that something else did would be incomparably higher. That is not an indictment of science. It is a description of how scientific consensus actually moves slowly, conservatively, with enormous resistance to conclusions that require rewriting foundational assumptions. In most cases, that conservatism is a feature, not a flaw. It prevents false positives. It demands rigorous verification before extraordinary claims are accepted. But it also means that if a genuine nuclear technosignature were present in the geological record present, measurable, chemically unambiguous, the institutional pathway from discovery to accepted conclusion would be long, painful, and heavily contested at every step. The first researchers to report it would face years of scrutiny, replication demands, and alternative explanation proposals before the data was allowed to mean what it plainly meant. We have been through this pattern before in science. Continental drift was dismissed for decades after Wegener proposed it in 1912. The asteroid impact hypothesis for the Cretaceous-Paleogene extinction was aggressively resisted for years after Alvarez published in 1980. Paradigm shifts do not arrive smoothly. The geological record has now given us anomalous carbon isotopes at the PETM, anomalous fossil emergence rates in the Cambrian, anomalous organic chemistry in deep ocean cores, and radiogenic isotope spikes in polar ice that are not fully explained. Each one individually has a candidate natural explanation. Together, they form a pattern that the Silurian hypothesis framework predicted would exist if something technological had operated on this planet before us. We have moved through the rock, through the chemistry, through the nuclear physics embedded in ice and sediment. But now we go up, into the atmosphere, into the ancient frozen archive of the poles. And what is locked inside that ice is larger than everything in this first act combined. The Antarctic ice core retrieved by the European Project for Ice Coring in Antarctica, known as EPICA, is the most precise and complete climate archive that exists on this planet. Drilled to a depth of 3,270 meters at Dome C in East Antarctica, the EPICA core contains 800,000 years of continuous atmospheric and climate data, preserved layer by layer in compressed ice. Every snowfall that landed on that location for the last 800 millennia left a chemical record. Trapped air bubbles preserve samples of the actual atmosphere from each era. Isotopic ratios in the ice crystals record temperature at the time of deposition. Dust particles record wind patterns and volcanic activity. It is not a proxy for Earth's climate history. It is a direct physical sample of it, pulled out of the ground in a tube. What 800,000 years of continuous data reveals is a clear, cyclical pattern. 8 glacial cycles, each lasting roughly 100,000 years, each following a recognizable rhythm of slow cooling into full glaciation, followed by a rapid warming into interglacial conditions. The pattern is driven primarily by variations in Earth's orbit and axial tilt, the Milankovitch cycles, which modulate how much solar energy reaches different latitudes at different times of year, gradually building or melting continental ice sheets over tens of thousands of years. The system is not perfectly regular, but it is broadly predictable. And within the EPICA record, it mostly behaves as the orbital mechanics predict. Mostly, Milankovitch cycles operate like a cosmic calendar, an astronomical clock, running on the gravitational interactions between Earth, the Moon, Jupiter, and the Sun, ticking out ice ages and warm periods on timescales of tens to hundreds of thousands of years. The clock is precise. Astronomers can calculate it backward with high confidence. Paleoclimatologists use it to predict when glaciations should begin and end, and the predictions generally match the ice core record well. But occasionally, the clock appears to have been adjusted early. Temperature rises and carbon dioxide increases appear in the EPICA record ahead of when the orbital forcing would be expected to initiate them, as though the warming was already underway before the astronomical trigger arrived to take credit for it. 3 anomalous intervals in the EPICA data stand out in the published literature. The transitions at approximately 400,000 years before present and 650,000 years before present show temperature and carbon dioxide increases that precede the calculated orbital forcing by margins that exceed the uncertainty in the age model. A 2023 analysis, published in Nature, re-examining the EPICA chronology with updated dating methods, confirmed that these forcing anomalies are real features of the data rather than artifacts of age model uncertainty, and acknowledged that their precise causal mechanism remains incompletely explained. The authors proposed candidate natural mechanisms, internal ocean circulation feedbacks, methane release from permafrost, dust albedo interactions. These are legitimate hypotheses. What the paper also stated, in the careful language of peer-reviewed climate science, is that none of them fully closes the gap between the expected timing of orbital forcing and the observed onset of warming in those intervals. Something warmed the planet before the orbital calendar said it should warm, and the magnitude of the early forcing, when translated into energy units, is not small. Now consider what modern science is actually doing with climate systems right now, in the 2020s. Harvard University's Solar Geoengineering Research Program is actively developing and testing stratospheric aerosol injection, a technique that involves releasing reflective particles into the upper atmosphere to reduce incoming solar radiation and lower global temperatures. The program has conducted real-world experiments, including the Stratospheric Controlled Perturbation Experiment, which has faced significant controversy and, in some cases, political opposition precisely because the scientific community recognizes that injecting aerosols into the stratosphere constitutes a genuine intervention in the planetary climate system with potentially global consequences. Cloud seeding, the deliberate modification of precipitation patterns by introducing silver iodide or other nucleating agents into clouds, is already operational in multiple countries, including the United States, China, and the United Arab Emirates. It is not experimental. It is infrastructure. Marine cloud brightening, ocean iron fertilization, direct carbon capture at industrial scale. These are not science fiction proposals. They are funded research programs at major institutions. The point is not that they work perfectly, or that humanity is currently managing Earth's climate. The point is that a civilization with several centuries more technological development than we currently have would be capable of interventions that would produce exactly the kind of anomalous forcing signatures visible in the Epocha record. The technology to move the climate ahead of its orbital schedule, to inject enough forcing into the system to initiate warming before the astronomical trigger arrives. That technology is not speculative. It is a more advanced version of what Harvard is testing right now in the stratosphere above New Mexico. If you could set Earth's thermostat to any temperature, what would you choose? Think about it seriously for a moment. Warmer means more agricultural land in Canada and Siberia, but less coastline and more extreme weather. Cooler means stable ice sheets and predictable monsoons, but shorter growing seasons at high latitudes, and every fraction of a degree affects rainfall, ocean currents, storm intensity, and ecosystem distribution across the entire planet. Simultaneously, the correct answer is almost certainly ask the other 8 billion people first, then negotiate for a century, then probably still disagree, which is precisely why geoengineering is the most contentious subject in contemporary climate science. Not because the technology does not work, but because no governance structure on Earth has the authority to make that decision on behalf of all humanity, and every intervention affects everyone whether they consented or not. The solar radiation reaching Arizona is the same solar radiation reaching Bangladesh. You cannot geoengineer for one country. If a prior civilization had reached the point of planetary climate intervention, and the Epocha anomalies suggest something may have forced the climate system ahead of its orbital schedule at least twice in the last 650,000 years, they would have faced exactly this governance problem, or they would not have. Perhaps that is the more unsettling possibility. Climate can be adjusted, but the atmosphere, the specific mixture of gases you are breathing at this exact moment, the evidence suggests it may have been fundamentally rebuilt from scratch, once, a very long time ago. And the numbers around that event do not add up cleanly. The oxygen in Earth's atmosphere right now measures 21%. It feels like a given. It feels like the natural state of the planet, the background condition against which all of Earth's history has unfolded. It is not. It is a relatively recent development in geological terms, and the way it got to 21% is one of the most dramatic and least fully explained transitions in the 4.5 billion year history of this planet. 2.4 billion years ago, Earth's atmosphere contained essentially no free oxygen, near zero. The early atmosphere was dominated by nitrogen, carbon dioxide, methane, and water vapor, a reducing atmosphere chemically hostile to the kind of aerobic life that now dominates every ecosystem on Earth's surface. Then, in what geologists call the Great Oxidation Event, oxygen levels in the atmosphere rose sharply, transforming the planet's chemistry, poisoning the anaerobic organisms that had dominated for 2 billion years, and setting the stage for every complex multicellular life form that followed. The cause, in the standard account, is cyanobacteria, ancient photosynthetic microorganisms that evolved the ability to split water molecules and release oxygen as a byproduct. Over millions of years, their cumulative output overwhelmed the geological sinks that had been absorbing free oxygen, and the gas began accumulating in the atmosphere. The mechanism is real. Cyanobacteria existed. Photosynthesis produces oxygen. The geological evidence for microbial mats predating the Great Oxidation Event is solid. What is less settled is the rate and the timing. Research published in Nature Geoscience through 2024 has continued to refine the chronology of the Great Oxidation Event and document something that was already known but imperfectly understood. The oxygen rise was not smooth. It was episodic. There were periods of sharp increase, followed by partial retreats, followed by further increases, a stepwise, irregular pattern that doesn't fit neatly with a simple model of cyanobacterial output, gradually accumulating over time. More specifically, within the broader geological record, oxygen level proxies show what researchers call whiffs brief, anomalous spikes of elevated atmospheric oxygen at time points before the main Great Oxidation Event, SAME, and at several intervals afterward, that exceed the baseline expected from the biological productivity of the era. Some of these spikes are well explained by specific geological events: volcanic outgassing changes, continental configuration shifts affecting nutrient delivery to oceans. Others sit in the literature as documented anomalies with proposed but not confirmed natural mechanisms. The pattern is consistent. Oxygen behaves mostly as the biology and geology predict, and then periodically does something unexpected. What makes the 21% figure so striking is how precisely calibrated it is for the requirements of complex life, particularly life that uses fire. Below approximately 17% atmospheric oxygen, combustion becomes nearly impossible. Wood will not ignite. Fire does not sustain. A civilization dependent on controlled combustion for cooking, for metallurgy, for any of the technological processes that require high heat cannot develop below that threshold. The entire trajectory from stone tools to bronze to iron to steam engines requires fire, and fire requires oxygen above 17%. Above approximately 25% atmospheric oxygen, the opposite problem occurs. Plant material becomes so easily ignitable that wildfires become self-sustaining at a global scale. Lightning strikes in a 25% oxygen atmosphere do not produce isolated forest fires. They produce continental conflagrations. The geological record from the Carboniferous period, when atmospheric oxygen may have briefly reached 35%, shows widespread charcoal deposits indicating massive, frequent wildfires across enormous areas. 21% sits almost exactly in the middle of that window, high enough for efficient aerobic metabolism and controlled combustion, low enough that fire remains a tool rather than an uncontrollable environmental force. It is, in the precise technical term, a Goldilocks value, and not just approximately, but quite precisely. No other planet in the solar system has free atmospheric oxygen at any concentration. Venus carbon dioxide and sulfuric acid. Mars less than 1% carbon dioxide. Negligible oxygen. Jupiter. Saturn. The gas giants hydrogen and helium with trace compounds. The 21% oxygen atmosphere of Earth is not just unusual in our solar system. It is, as far as planetary science currently knows, unique. David Grinspoon, astrobiologist at the Planetary Science Institute and author of Earth in Human Hands, has argued in published work and public scientific discourse that Earth's biosphere has effectively co-evolved with its atmosphere, that life and the chemical environment of the planet are so deeply intertwined that the boundary between biological process and planetary engineering becomes conceptually blurry. His framework, building on James Lovelock's Gaia hypothesis, but grounding it more explicitly in astrobiological science, suggests that Earth's atmospheric composition is not simply the background against which life happens. It is, in a meaningful sense, a product of life's activity over geological time. The question Grinspoon's framework opens without answering. And without claiming to answer is where precisely the line falls between a planetary atmosphere shaped by the cumulative, uncoordinated activity of billions of years of biological evolution, and one that was at some point deliberately modified by an agent capable of intentional atmospheric management. The geological signatures of those two processes, at sufficient temporal remove, may be indistinguishable with current analytical tools. Have you ever stopped to think that the air you are breathing right now might be a product of deliberate engineering? Not metaphorically, literally. The 21% oxygen, the 78% nitrogen, the trace gases that make this atmosphere suitable for your metabolism, your combustion, your civilization, none of that was guaranteed by physics. Earth could have been Venus. It could have been Mars. Something about the history of this planet produced an atmosphere calibrated, with remarkable precision, to the requirements of exactly the kind of life that now dominates it. Technically speaking, we are living inside a finely tuned life support system. Temperature, pressure, atmospheric composition, all dialed to values that fall within the narrow range where complex aerobic life and industrial civilization become possible. The manual for this system was apparently read very carefully by someone. Whether that someone was 4 billion years of unguided evolution, or something with more deliberate intent, the atmosphere itself cannot tell us directly. What it can tell us is that it was not always this way, and that the transitions that made it this way were faster, more episodic, and less completely explained than the standard account suggests. If the atmosphere is the product of design, then the mass extinctions that punctuate Earth's biological history may not have been accidents at all. They may have been the mechanism, the tool by which the design was implemented, one catastrophic reset at a time. 5 times in Earth's history, the biosphere has collapsed, not declined, not struggled, collapsed with 70 to 96% of all species on the planet, wiped from existence in intervals that, measured against the full sweep of geological time, are essentially instantaneous. The end Ordovician, 443 million years ago, the late Devonian, 372 million years ago, the end Permian, 252 million years ago, the end Triassic, 201 million years ago, the end Cretaceous, 66 million years ago. 5 resets, 5 near-total eliminations of the existing biological order, and after every single one, without exception, life returned more diverse than before, more structurally complex than before, operating on faster evolutionary timescales than the version it replaced. The post-extinction radiations are not just recoveries, they are upgrades. Each time the slate is cleared, whatever fills the vacuum is measurably more sophisticated, larger nervous systems, more complex behavioral repertoires, tighter ecological interdependencies, greater adaptability than the organisms that had occupied those ecological roles before the collapse. 5 collapses, 5 upgrades, each one producing a more neurologically advanced dominant life form than the last. At some point, the question stops being whether this is a coincidence and starts being what kind of process produces this specific pattern. The end Cretaceous extinction, the most studied, most precisely dated of the 5, offers the clearest window into what is actually strange about these events. 66 million years ago, an asteroid roughly 10 to 15 kilometers in diameter struck what is now the Yucatan Peninsula of Mexico at a location called Chicxulub. The impact released energy equivalent to billions of nuclear weapons simultaneously, triggered global wildfires, ejected enough particulate matter into the stratosphere to block sunlight for years, and collapsed photosynthesis-dependent food chains across the planet. Luis Alvarez, who received the Nobel Prize in Physics for work in particle physics, not geology, along with his son Walter Alvarez, proposed the impact hypothesis in 1980 based on the globally distributed iridium anomaly at the Cretaceous-Paleogene boundary. The hypothesis was initially controversial and is now broadly accepted as the primary mechanism of the extinction. Non-avian dinosaurs gone, pterosaurs gone, marine reptiles including mosasaurs and plesiosaurs gone, ammonites gone, roughly 76% of all species on Earth eliminated within a geologically brief interval following the impact. But coelacanth lineage fish survived, crocodilians survived, essentially unchanged. Freshwater turtles survived, sharks. Some lineages dating back hundreds of millions of years survived, small placental mammals. The ancestors of every mammal alive today, including humans, survived. Birds. The avian descendants of theropod dinosaurs survived and subsequently diversified into the most species-rich class of land vertebrates on the planet. The question that the extinction data raises, and that the standard impact model does not fully address, is why the pattern of survival looks the way it does. A 2022 study published in the Proceedings of the National Academy of Sciences analyzed selectivity patterns across the Cretaceous-Paleogene boundary in detail, examining which lineages survived, which went extinct, and whether the distribution of survivors was statistically consistent with random chance given the severity of the environmental disruption. It was not. The groups that survived the end Cretaceous extinction with the highest success rates were, disproportionately, the groups that would go on to form the ecological foundations of the Cenozoic world, the era that followed, and that ultimately produced us, small-bodied generalist mammals, capable of dietary flexibility and rapid reproduction, freshwater species buffered from the immediate marine productivity collapse, bird lineages with traits suited to the post-impact landscape, crocodilians, whose physiology allows extended dormancy during food scarcity. The survivors were not random. They were, with a frequency that exceeds chance expectation, precisely the organisms that the next phase of biological history required as its starting material. This does not prove selection. Non-random survival patterns can emerge from the specific nature of the killing mechanism and impact winter that favors certain physiologies over others. Marine anoxia that hits some ocean zones harder than others. Fire that eliminates large-bodied terrestrial animals preferentially. These are legitimate mechanistic explanations for differential survival. What cannot be dismissed easily is that the same basic pattern appears across all 5 major extinction events. In each case, the groups that collapse are the groups that had dominated the previous era. In each case, the groups that survive in anomalously high proportions are the groups that form the ecological scaffolding of the next era. In each case, the post-extinction radiation produces organisms with measurably greater neural complexity than the pre-extinction dominant fauna. Extend this pattern across the full 500 million year record of complex animal life and graph one variable average neural complexity of the dominant life form in each geological era. The resulting curve does not increase smoothly. It is flat for long periods, then spikes sharply upward immediately following an extinction boundary, then flattens again, then spikes again at the next boundary. The spikes and the extinction events are the same moments. Every jump in neural complexity in the history of animal life on this planet coincides with a mass extinction. The progression from simple nervous systems to fish brains, to amphibian brains, to reptilian brains, to mammalian brains, to primate brains is not a gradual ramp. It is a staircase, and each step up is preceded by a collapse of whatever occupied that step before. If you were designing a system to produce increasingly complex cognition over geological timescales, if you wanted to write an algorithm for generating intelligence through biological evolution, this is approximately what that algorithm would look like. Iterate, stress test, eliminate the current generation, select the most promising survivors, accelerate the next iteration, repeat. If you were the planetary designer, would you choose this method? It is worth thinking through honestly. It is extraordinarily slow by human standards, hundreds of millions of years to get from sponges to mammals. It is extraordinarily wasteful, 96% mortality at the end Permian alone, representing hundreds of millions of species of creatures with some degree of sentient experience, gone. It is brutal in a way that is difficult to reconcile with any conventional notion of benevolent design. But it works. Whatever its moral character, the method demonstrably produces results. Each iteration is more capable than the last. Each reset clears the constraints that the previous dominant life form had imposed on the ecosystem and opens space for something with different capabilities to emerge. If Earth were a research and development project, and that framing is uncomfortable precisely because it fits the data so well, then the dinosaurs were clearly a prototype that was recalled after 165 million years of field testing to make room for the next model. We are version 6.0 of that project. The feature set is considerably more advanced than any previous build. Whether this should be reassuring or alarming probably depends on whether you think the project has a completion date. We have looked at the history of life from above the patterns in the fossil record, the selectivity of extinctions, the algorithmic progression of neural complexity across geological time. Now we go in the opposite direction, down, through the ice, below the surface of the most remote continent on Earth, where radar has found something that the maps did not predict. In 2016, NASA's Operation Icebridge, an airborne survey mission using ice-penetrating radar to map the Antarctic ice sheet from above, announced the confirmed discovery of a massive subglacial canyon system hidden beneath the West Antarctic ice sheet. The canyon had been invisible to surface observation. It is buried under 2 to 3 kilometers of solid ice, but radar sees through ice the way X-ray sees through skin. And what the radar returned was unambiguous. A canyon system larger than the Grand Canyon, running for hundreds of kilometers beneath the ice, with walls dropping over 1 kilometer from rim to floor. NASA published the findings in official communications. The data was real. The survey methodology was standard remote sensing science, and the discovery was uncontested. Antarctica, it turned out, was not the featureless frozen plateau that surface observation suggested. Under the ice was an entire hidden continent with its own mountains, valleys, lake systems, and topographic complexity that no human being had ever seen and that existing maps had rendered almost entirely blank. The British Antarctic Survey has since produced 2 successively more detailed subglacial topographic maps, BedMap 2 and BedMap 3, synthesizing radar data from decades of airborne and ground-based surveys across the entire Antarctic continent. What those maps reveal is a landmass of extraordinary geological complexity, almost entirely concealed beneath an ice sheet averaging 2 kilometers in thickness and reaching 4 kilometers at its deepest points. The subglacial landscape includes mountain ranges comparable in scale to the European Alps. It includes deep basins that sit below sea level. It includes river valleys and what appear to be ancient drainage networks carved by liquid water, evidence that the landscape beneath the ice was once exposed to surface conditions and flowing rivers before glaciation buried it. Most remarkably, it includes lakes, not ancient frozen remnants, but active liquid water subglacial lakes, kept liquid by geothermal heat from below and insulated from the freezing temperatures above by kilometers of ice. BedMap data has identified over 400 subglacial lakes beneath the Antarctic ice sheet. The largest is Lake Vostok. Lake Vostok sits beneath Russia's Vostok Station in East Antarctica, under approximately 4 kilometers of ice. It is roughly 250 kilometers in length and 50 kilometers in width, comparable in surface area to Lake Ontario. The water in it has been isolated from the surface atmosphere for somewhere between 15 million and 25 million years, sealed under ice that formed as Antarctica glaciated during the Miocene epoch. In 2012, A Russian drilling team reached the lake's surface after more than 2 decades of drilling through the overlying ice. The project was technically extraordinary and scientifically controversial. The contamination risk to a pristine, isolated ecosystem was significant, and the international scientific community debated the ethics of the penetration at length. When the drill finally reached water, samples were recovered and analyzed. NASA, in assessments of the Lake Vostok project, confirmed that the chemical conditions within the lake are not incompatible with microbial life, that the geothermal energy input, the liquid water, and the available chemical nutrients could theoretically sustain a biosphere that has been evolving in complete isolation for tens of millions of years. Whether life is actually present in Vostok remains an open scientific question, because definitive contamination-free sampling has not yet been achieved. A lake the size of Lake Ontario, liquid, biologically plausible, sealed from the surface world for up to 25 million years. Whatever is in that water has not been in contact with the rest of Earth's biosphere since before the earliest hominids existed anywhere on the planet. Lake Vostok has achieved, entirely by geological accident, the most thorough social distancing in the history of life on Earth. The microorganisms in that water, if they exist, have had no news from the outside world in 25 million years. By this point, they have probably stopped waiting for updates. The bedmap data contains one category of features that has drawn attention from geophysical researchers and remains in the published literature without definitive interpretation. Scattered across the subglacial topographic maps are angular features, straight edges, sharp corners, geometric regularities that do not match the expected signature of either tectonic fracturing or glacial erosion. Both of those processes produce their own characteristic shapes. Tectonic features tend towards specific angular geometries determined by the crystalline structure of the rock. Glacial erosion produces rounded valleys, striated surfaces, and characteristic U-shaped cross-sections. The anomalous angular features in certain bedmap sectors match neither profile cleanly. Geophysical research groups studying the bedmap data have flagged these features as requiring further investigation. No conclusion has been reached. The most conservative interpretation that they represent unusual tectonic fracture patterns or erosion under conditions not fully captured by current glaciological models has not been ruled out. Neither has any alternative interpretation been formally established. They sit in the literature as documented anomalies awaiting better data. What makes them relevant to the broader question is this: 34 million years ago, Antarctica was not glaciated. The continent was ice-free, with temperatures sufficient to support vegetation and animal life. Fossil evidence confirms forests of Nothofagus southern beach and diverse fauna including early marsupials and primitive ungulates. In the geological record from pre-glacial Antarctica, a continent with a temperate climate, exposed land surface, liquid water, and tens of millions of years of biological habitability, by the same reasoning applied to the rest of Earth's surface, was not, in principle, inhospitable to the development of complex civilization. When the glaciation began and the ice advanced, it would have buried whatever existed on that surface under kilometers of ice, and it would have preserved it frozen, sealed from oxidation, protected from erosion in conditions that are, for certain materials, extraordinarily conserving. If you could drill into any single point on Earth's surface in search of evidence, where would you choose? The ocean floor offers the deepest sediment record, but recovery is technically demanding, and the sediment environment is chemically active over long time scales. The continental cratons of Africa and Australia preserve the oldest surface rocks, but surface exposure means billions of years of weathering. The ice of Antarctica covers a continent that was habitable until 34 million years ago, preserves materials in a cold, dry, low-oxygen environment, and has been systematically surveyed only in the last 2 decades with tools capable of seeing through the ice. 4 kilometers of ice is not an obstacle. It is a preservation medium. And 4 kilometers of natural cold storage, over 34 million years, is a better archive than anything humans have ever deliberately engineered. Beneath the ice is rock. Beneath the rock is the geological record. But there is something smaller than rock, smaller than any molecule visible to the naked eye, small enough to be written directly into the DNA of every living organism on this planet. And what has been found there is the strangest data point in this entire story. In 2017, a research team at the University of Washington accomplished something that reframed the entire question of what DNA actually is. They took a short digital video file, a few seconds of footage, converted it into a DNA sequence using a computational encoding scheme, synthesized that sequence as actual physical DNA molecules, stored those molecules, and then sequenced them back. The recovered video was perfect. No data loss, no corruption. A digital file had been written into the molecular structure of life itself, stored as chemistry rather than electronics, and read back with complete fidelity. In 2021, Microsoft Research published a comprehensive assessment of DNA as a data storage medium. The number they arrived at was one that required reading twice. 1 gram of DNA can store 215 petabytes of data. To put that in proportion, 215 petabytes is roughly equivalent to the entire content of the internet at the time of writing. Every web page, every video, every database, every image, every file stored on every server on Earth, compressed into a volume of material you could hold between 2 fingers. No silicon chip comes close. No magnetic drive. No optical disk. No quantum memory system currently in development approaches that storage density. DNA is not just an efficient storage medium. By the known laws of physics and chemistry, it is the most efficient storage medium that matter allows. Which means that when biologists call DNA the blueprint of life, they are describing only one of its properties. The other property, the one that the University of Washington and Microsoft Research demonstrated empirically, is that DNA is an information storage architecture of extraordinary capacity, extraordinary fidelity, and extraordinary durability. These are not the same thing as being a biological blueprint. They are the properties of a data system. The question that follows from this is one that mainstream biology has not historically needed to ask, but that the storage density numbers now make unavoidable is all of that capacity being used exclusively for biological instructions. The answer, based on what genomics has found over the last 2 decades, is genuinely uncertain. For most of the 20th century, scientists assumed that the portions of the genome not directly encoding proteins were essentially functionless accumulated evolutionary noise, broken genes, repetitive sequences with no active role. They called it junk DNA. The term reflected genuine scientific consensus. Roughly 98% of the human genome does not code for proteins, and for decades, that non-coding majority was treated as the genomic equivalent of an attic full of broken furniture. The ENCODE project, the Encyclopedia of DNA Elements, a large-scale consortium effort coordinated across dozens of research institutions, systematically mapped the functional activity of the human genome. Their landmark analysis, published in Nature in 2012, updated and expanded in 2020, produced a finding that forced a significant revision of the junk DNA framework. At least 80% of the human genome shows biochemical activity of some kind. It participates in gene regulation, chromatin structure, RNA production, or other cellular functions. It is not inert. 80% functional. That leaves roughly 20% that the ENCODE data did not assign a clear regulatory role. And within that remaining fraction, there are categories of sequence highly repetitive elements, certain classes of non-coding RNA genes, palindromic sequences that appear and reappear across the genomes of wildly different species, whose function remains genuinely unclear. In 2013, a paper published in the journal Icarus, the peer-reviewed journal of the International Society for the Study of the Origin of Life, affiliated with the Carl Sagan Institute, proposed a hypothesis that placed this genomic uncertainty into a different frame entirely. The authors, including researchers affiliated with institutions in Kazakhstan, suggested that certain highly conserved, repetitive non-coding sequences in the human genome showed mathematical properties more consistent with an intentional numerical code than with the statistical patterns produced by random mutational drift or known biological selection pressures. They proposed, carefully and with explicit acknowledgement, that the hypothesis was speculative, that these sequences might represent a form of encoded message, a genomic signal inserted into the genome of early life and preserved through billions of years of biological inheritance. The paper did not claim proof. The hypothesis has not been confirmed by subsequent research, and it remains a minority position not accepted by mainstream genomics. What it represents is a formally published, peer-reviewed scientific proposal that the non-coding genome may contain information whose origin and function are not fully explained by current biology. That is a meaningful distinction from fringe speculation. Now set that alongside what is known about DNA's survival properties. A 2021 study published in Nature reported the recovery and partial sequencing of genetic material from dinosaur specimens preserved in amber fossilized tree resin dating to approximately 100 million years before present. The DNA was degraded, fragmented, and incomplete. But it was recoverable. Sequences could be read. The molecular information, locked in the amber matrix, had survived 100 million years of geological time in a form that modern sequencing technology could partially decode. 100 million years. The amber had acted as a perfect preservation medium, sealing the biological material from water, oxygen, and microbial activity, the three primary agents of DNA degradation. Under amber-preserved conditions, the polymer backbone of DNA is stable over timescales that dwarf the entire history of human civilization by a factor of 50,000. Hold those two facts together. DNA can store 215 petabytes per gram. DNA preserved in amber survives for 100 million years in readable form. And the genomes of living organisms contain vast regions of sequence whose function is not fully accounted for by current biological models. If you wanted to send a message across 100 million years, not to a specific recipient, not to a specific location, but to whatever form of intelligence eventually developed on this planet, what would you use as your medium? Stone erodes, metal corrodes, organic structures degrade, synthetic polymers fragment. Every physical substrate fails at sufficient temporal scale, except one. The only medium that geological time cannot destroy, because geological time has no mechanism for destroying it as long as it exists inside a living organism that continues to reproduce, is DNA itself. As long as life continues, the genome continues to be copied, generation after generation, carrying its full sequence coding regions and non-coding regions alike forward through time with extraordinary fidelity. A message written into the non-coding genome of a widely distributed, highly resilient species would be replicated billions of times across billions of generations. It would survive extinction events in the genomes of the survivors. It would persist through continental drift, ice ages, atmospheric changes, and every other geological upheaval, as long as at least some carriers of the sequence remained alive somewhere on the planet. If you wanted to leave a message for a civilization 100 million years from now, what would you write? Think about that honestly. Not what you would want to say, but what would actually matter. What is important enough, universal enough, and compact enough to be worth encoding in a medium that cannot be updated. cannot be retrieved on demand and will be read if it is ever read by minds that cannot be predicted. That is a genuinely hard design problem, and the answer might already be somewhere in the 37 trillion cells of your body, written in a language whose grammar no one has yet learned to read. We are spending hundreds of billions of dollars building data centers across the American Southwest server farms the size of small cities, cooled by industrial air conditioning, powered by dedicated electrical substations, requiring constant maintenance and hardware replacement every few years. Meanwhile, every human being on Earth is already carrying a 3 billion base pair storage drive that operates at room temperature, runs on 20 watts of metabolic energy, replicates itself with error rates below 1 in 10 billion, and has been in continuous operation for 3.8 billion years without a single hardware failure. Evolution built cloud storage long before Amazon Web Services filed its first patent. The infrastructure was already here. The only question is whether it is storing more than we know. We have traveled from rock to ice to the molecular architecture of life itself. Act 3 takes us somewhere larger into the Earth's deep interior, out to the edges of the solar system, and finally, to the question that reframes everything that came before it, if they were here. Where are they now? The answer may be closer than any map has ever shown. In 2022, research published in Nature Communications confirmed something that sounds like it belongs in a physics laboratory decades from now, but is already being engineered into commercial products. Today, quartz crystals can store data in 5 dimensions, 5 independent axes of optical information encoded into the molecular structure of the crystal lattice, with a theoretical storage lifespan of 13.8 billion years at room temperature. 13.8 billion years. That is the current estimated age of the observable universe. A quartz crystal encoded with data today would still be readable, in principle, when the universe is twice its current age. This is not a theoretical proposal. Microsoft, in partnership with the optical storage company, now operating under the Optica brand, has been actively developing 5-dimensional quartz storage as a commercial archival medium. The physics works. The encoding and retrieval systems work. The durability has been empirically verified under accelerated aging tests. The technology exists, and it is moving from laboratory demonstration toward industrial deployment. Now consider what the crust of the Earth is made of. Quartz silicon dioxide in crystalline form is the second most abundant mineral in Earth's continental crust. Every beach on every continent is composed primarily of quartz grains, the product of billions of years of rock weathering, reducing quartz-bearing granite and sandstone to individual mineral particles. The total mass of quartz in Earth's crust is not precisely known, but conservative geological estimates place it in the range of hundreds of trillions of tons. Likely more. The number is so large that it resists intuitive comprehension. It is a planetary quantity, measured in units that ordinary human experience has no frame for. The planet is, in a literal and chemically precise sense, wrapped in a shell of the most durable data storage material that physics allows. What makes this more than an interesting coincidence is the other property of quartz that electronics engineers have depended on for a century: piezoelectricity. When mechanical pressure is applied to a quartz crystal, it generates an electrical voltage. When an electrical voltage is applied to a quartz crystal, it vibrates at a precise, reproducible frequency determined by the crystal's geometry and cut. This is the operating principle of every quartz clock and watch ever manufactured. The crystal oscillates at a known frequency, and the electronics count those oscillations to keep time. It is also the principle underlying the oscillators in virtually every digital computing device ever built. The precision of modern electronics depends fundamentally on the piezoelectric properties of quartz. The relationship is bidirectional. Mechanical stress produces electrical signal. Electrical signal produces mechanical oscillation, The crystal converts between mechanical and electrical energy with extraordinary efficiency and extraordinary precision. Now apply that property to a geological scale. Earth's crust is fractured by a global network of fault systems, the tectonic plate boundaries and intraplate fault zones that collectively span hundreds of thousands of kilometers and penetrate deep into the lithosphere. These fault systems run through rock that is, in enormous proportion, quartz-bearing. Every seismic event, every earthquake, every tremor, every microseismic event too small for human perception propagates mechanical stress waves through that quartz-rich rock matrix. By the physics of piezoelectricity, that mechanical stress is accompanied by electrical field generation throughout the surrounding crystal structure. The global fault network is, from a purely physical standpoint, a planetary scale piezoelectric array. Mechanical information, the pressure signatures of tectonic movement, seismic wave propagation, stress accumulation and release propagates through it continuously, accompanied by electrical field fluctuations that travel through the conductive rock matrix at speeds determined by the electrical properties of the surrounding geology. It is not a designed computer. It is not a circuit in any engineered sense, but it is a physically real system that transmits and processes both mechanical and electromagnetic information at a planetary scale, continuously, using the piezoelectric properties of one of the most abundant minerals on Earth's surface. The Schumann resonances make this planetary electromagnetic activity measurable from the surface. Named after the German physicist Winfried Schumann, who predicted them mathematically in 1952. The Schumann resonances are electromagnetic standing waves that form in the cavity between Earth's surface and the lower boundary of the ionosphere. The fundamental frequency is 7.83 Hz, a number NASA has studied and confirmed. Represents a stable, globally coherent electromagnetic oscillation maintained by the continuous electrical activity of thunderstorms and other electromagnetic sources distributed across the planet. It has been called, informally but accurately, the electromagnetic heartbeat of the Earth. What is scientifically documented, but not yet fully explained, is that anomalies in the Schumann resonance pattern, deviations from the expected frequency and amplitude, have been recorded in the hours and days preceding major seismic events. The correlation has been noted in peer-reviewed geophysics literature and is an active area of research, with proposed mechanisms involving ionospheric perturbations caused by stress-induced electromagnetic emissions from rock under increasing tectonic pressure. The mechanism is not fully established. The correlation is real enough to be worth investigating. Have you ever considered that the Earth might be thinking in some sense of that word, not metaphorically, physically, a system that processes information, that converts mechanical state changes into electrical signals, that maintains coherent electromagnetic oscillations at a global scale, that shows measurable electromagnetic precursors to major physical events by some functional definitions of information processing? That description fits the planetary system we are living on. When you pick up a piece of quartz from a riverbed, a smooth, translucent pebble that weighs almost nothing in your palm, you are holding a storage medium with a theoretical lifespan greater than the current age of the universe. Apple's best solid-state drives are rated for 10 years. The quartz you found in a creek outlasts the cosmos. Every technology company on the planet should feel at least mildly embarrassed. If data is being stored in the geology of the Earth itself, then the next question is who built the network capable of reading it? And the answer to that question may be located somewhere that humanity has explored less thoroughly than the surface of Mars. We have mapped 100% of the Moon's surface. We have produced detailed topographic charts of Mars accurate to within meters. We have radar imaged the surface of Venus through its opaque cloud cover. We have sent probes to the outer planets and returned images of Pluto's nitrogen ice plains from 5 billion kilometers away. 20%. That is the fraction of Earth's own ocean floor that has been mapped with high-resolution bathymetric data equivalent to what we routinely produce for other worlds. The remaining 80%, covering an area larger than the total land surface of all Earth's continents combined, is known primarily from low-resolution satellite gravity measurements that reveal broad topographic features, but miss anything smaller than a few kilometers in scale. What is down there, in detail, at the resolution that would reveal structures, formations, or anomalies at the scale of buildings or geological features of comparable size, is simply unknown. We have better maps of the dark side of the moon than of the floor of the Pacific Ocean. The Mariana Trench descends to 11,034 meters below sea level. At its deepest confirmed point, the Challenger Deep, Mount Everest, at 8,849 meters above sea level, would fit inside it with more than 2,000 meters of water to spare. The pressures at that depth reach approximately 1,100 atmospheres, 1,100 times the pressure at sea level. The temperature is just above freezing. No sunlight reaches it, no photosynthesis occurs there. We know the surface chemistry of Mars in greater chemical detail than we know the geology of the Challenger Deep. One human being has ever descended to the full depth of the Mariana Trench in a crewed vessel. That person was James Cameron in 2012, in a vehicle he largely funded himself. The director of Titanic and Avatar has been deeper into Earth's ocean than any NASA astronaut, any oceanographic institution, any government-funded scientific program has managed to achieve with a human crew. NASA's budget in 2023 was approximately $25 billion. The total cumulative investment in crewed deep ocean exploration to the full depth of the Hadal Zone across all nations and institutions combined is a small fraction of a single year of that figure. The institutional priorities of human civilization have been, for the entirety of the space age, oriented outward rather than inward. The most unexplored frontier on Earth is Earth itself. The Lunar Reconnaissance Orbiter, operating since 2009, has produced the highest resolution maps of the Moon ever made. Among its most significant findings are extensive systems of lava tubes, subsurface tunnels formed when the outer crust of ancient lava flows solidified while molten rock continued to flow through and eventually drained out, leaving hollow conduits behind. Some of these lunar lava tubes have estimated diameters of up to 1 kilometer and extend for hundreds of kilometers beneath the lunar surface. The European Space Agency has formally identified them as priority candidates for human settlement, specifically because they provide natural shielding against the solar radiation, micrometeorite impacts, and temperature extremes that make the lunar surface hostile to sustained habitation. A lava tube on the Moon is, architecturally, a ready-made pressurizable habitat requiring no excavation. Mars presents a parallel situation with an additional anomaly. The Curiosity and Perseverance rovers have confirmed, through direct geochemical analysis of Martian rock, that Mars once had liquid water on its surface, a substantially thicker atmosphere, and conditions compatible with the chemistry of life. What the rover data and orbital spectrometry have also revealed, in findings published in Nature in 2019 and subsequently confirmed by additional analysis, are episodic methane spikes in the Martian atmosphere brief, localized increases in methane concentration that appear and disappear on timescales of days to weeks. Methane is chemically unstable in Mars' oxidizing atmosphere. Ultraviolet radiation breaks it down within a few hundred years. The fact that methane is detectable at all means it is being produced continuously by some active source. The two candidate mechanisms are geological serpentinization reactions between water and rock that can generate methane abiotically, and biological methanogenic microorganisms producing methane as a metabolic byproduct, as they do in Earth's wetlands and digestive systems. neither explanation has been definitively confirmed. The source of Martian methane remains an open scientific question. At Ceres, the largest object in the asteroid belt between Mars and Jupiter, classified as a dwarf planet and surveyed by NASA's Dawn spacecraft between 2015 and 2018, the cameras detected bright spots on the floor of Okator crater that were visible from orbit. Analysis determined the bright material to be sodium carbonate and other evaporate salts, deposited by briny water rising from a subsurface reservoir and evaporating at the surface. The chemical identification is established. What has not been fully explained is the geometric distribution of the brightest deposits. Their spatial arrangement within the crater floor shows a degree of regularity that planetary geologists continue to study. Return now to Earth's own deep ocean and to what lives there. Hydrothermal vent systems discovered in 1977 by researchers using the submersible Alvin along the Galapagos Rift are among the most remarkable environments ever found on this planet. Superheated water, reaching temperatures of 400 degrees Celsius and carrying dissolved minerals from the underlying rock, vents through fissures in the ocean floor and rapidly cools upon contact with near-freezing ambient water. Precipitating mineral towers that can grow to heights of 60 meters. Around these vents, entire ecosystems flourish tube worms up to 2 meters in length, chemosynthetic bacteria, shrimp, crabs, octopuses, all operating without any input of solar energy, sustained entirely by the chemical energy of the vent fluid. The pressures at hydrothermal vent depths reach 400 atmospheres. The ambient temperature of the surrounding water is between 2 and 4 degrees Celsius. The chemical environment is rich in hydrogen sulfide, heavy metals, and other compounds toxic to surface life. And life there is extraordinarily abundant. A civilization that needed to survive a surface catastrophe, an impact event, a runaway atmospheric change, a nuclear exchange, any of the mechanisms that have punctuated Earth's biological history would find in the deep hydrothermal vent environment everything required for long-term, independent survival: thermal energy, chemical energy, mineral resources, complete isolation from surface conditions, access to the global oceanic circulation system for material transport, and near-perfect concealment from any surface-based observation. If you had to choose between hiding in a lunar lava tube or at the bottom of the ocean, which would you pick? The moon offers radiation shielding and isolation from Earth's geological activity. The deep ocean offers thermal energy, chemical resources, biological productivity, and 80% of its floor unmapped by any instrument capable of detecting structures at the scale of buildings. Humanity has spent $500 billion reaching for the stars. James Cameron reached the deepest point on Earth with a custom submersible and a filmmaker's budget. If something had retreated to the deep ocean floor millions of years ago, and if our exploration priorities had remained what they are today, we would have essentially no systematic method of finding it. But beyond all the structures, beyond all the physical traces and the unexplored terrain, there is evidence that someone deliberately left a message. Not in stone, not in chemistry, not in DNA. A message about inevitability, about the cycle that every civilization eventually confronts. In the summer of 1950, Enrico Fermi, one of the architects of the first nuclear reactor, a man whose instincts about physics were essentially never wrong, sat down to lunch with colleagues at Los Alamos and asked a question so simple it took decades for the scientific community to fully reckon with its weight. Where is everybody? If the universe is 13.8 billion years old, and if even a small fraction of the hundreds of billions of stars in the Milky Way harbor planets capable of supporting life, and if even a tiny fraction of those planets produce civilizations capable of interstellar communication, then the galaxy should be full of signals, full of evidence, full of the electromagnetic exhaust of technological civilizations that have had billions of years longer than us to develop and expand. The sky is silent. That silence has a name, the Great Silence. And it may be the most important data point in the history of science, not because of what it tells us, but because of what it refuses to tell us, and what that refusal implies. The SETI Institute has been listening systematically since the early 1960s, 6 decades of radio telescope surveys, covering an enormous range of frequencies and sky directions, using instruments of steadily increasing sensitivity. The result is a database of null results, signal after signal, star after star, galaxy after galaxy, returning nothing that unambiguously indicates technological origin. 6 decades of silence from a universe that should, statistically, be talking. Except for 72 seconds on August 15th, 1977. That evening, the Big Ear radio telescope at Ohio State University recorded a signal of such unusual intensity and frequency characteristics that the astronomer reviewing the data printout circled it and wrote "Wow" in the margin, which is why it has been called the WOW signal ever since. It arrived from the direction of the constellation Sagittarius at a frequency close to 1,420 megahertz, the emission frequency of neutral hydrogen. Long considered by SETI researchers the most logical frequency for an intentional interstellar beacon, because any civilization with radio astronomy would know it. The signal lasted 72 seconds, which was the full duration of the telescope's observation window as Earth's rotation moved the antenna past that region of sky. It has never been detected again. No confirmed natural astrophysical source has been identified that could produce it. It remains, nearly 50 years later, unexplained. One signal, 72 seconds, never repeated. Robin Hanson, economist and theorist at George Mason University, formalized the implications of the Great Silence in 1998 with what he called the Great Filter. The idea that somewhere along the developmental pathway from simple chemistry to interstellar civilization, there exists a barrier so difficult to cross that virtually no species crosses it successfully. The Great Filter is whatever kills civilizations before they filled the galaxy. Its existence is implied by the emptiness of the sky. The terrifying question, the one that Hansen posed, and that has not been resolved in the quarter century since, is whether the Great Filter lies behind us or ahead of us. If it lies behind us, we are among the extraordinarily lucky survivors of a barrier that destroys almost all life before it reaches our stage, the development of eukaryotic cells, or of multicellular life, or of complex nervous systems, any of these transitions. So improbable that almost no planet achieves them, could be the filter. If so, the silence of the sky reflects not future doom, but past statistical improbability that we somehow cleared. We are the lucky ones. If the Great Filter lies ahead of us, the silence of the sky is a graveyard. Every technological civilization that has ever existed in the Milky Way reached our approximate level of development and then stopped, permanently, not because of external catastrophe, but because of something internal to the trajectory of technological civilization itself. Something that advanced species do to themselves, reliably, before they reach the stars. The historical record of human civilization on a smaller scale offers an uncomfortable pattern. Sumer, the first urban civilization, originator of writing and codified law, collapsed around 2004 BCE after centuries of soil salinization from over-irrigation depleted agricultural productivity. Egypt's Old Kingdom, which built the pyramids, collapsed around 2150 BCE during a prolonged drought that historians now attribute to a major volcanic eruption affecting global climate. The Western Roman Empire, which at its height administered 60 to 70 million people across 3 continents, Fragmented across the 5th century CE after centuries of overextension, resource depletion, and climate deterioration, the classic Maya civilization, which produced sophisticated astronomy, mathematics, and architecture across the Yucatan Peninsula, underwent rapid depopulation beginning around 850 CE, driven by a combination of prolonged drought and agricultural overextension. Every one of these collapses followed the same basic trajectory: rapid development, peak complexity, resource overextension, climatic stress, fragmentation. Not one of them saw it coming clearly enough to stop it. The acceleration of human technological development makes the pattern more acute, not less. From the controlled use of fire to the development of agriculture took approximately 300,000 years. From agriculture to the Industrial Revolution took approximately 10,000 years. From the Industrial Revolution to artificial intelligence took approximately 200 years. Each phase is roughly 30 times faster than the one before it. The curve is not linear, it is exponential. And exponential curves, extended far enough, produce outcomes that intuition cannot prepare for. From artificial intelligence to what we do not know. And that is precisely the point. We are at the inflection moment of the fastest phase of development in the history of our species, with technologies emerging faster than the social, political, and ethical frameworks capable of governing them can be built. The Bulletin of Atomic Scientists has maintained the doomsday clock since 1947, when it was created by the scientists who built the atomic bomb as a measure of humanity's proximity to self-inflicted civilizational catastrophe. In January 2024, the clock was set to 90 seconds to midnight, closer to the symbolic end than at any point in its 77-year history. Closer than during the Cuban Missile Crisis. Closer than during the height of the Cold War nuclear arms race. Do you think the Great Filter is behind us or ahead? Take a moment with that question. It is not rhetorical. Good news, we still have 90 seconds. Bad news, that is a metaphor. Better news, metaphors do not detonate. Worse news, what the metaphor represents can. If civilizational collapse is a cycle, did the civilization before us see it coming? And if they saw it coming, did they prepare anything? The answer may be yes, and we may already be part of that preparation without knowing it. In 2023, both Google DeepMind and OpenAI published major research addressing what the artificial intelligence field calls the alignment problem. The challenge of ensuring that increasingly capable AI systems reliably protect human values rather than optimizing for objectives that diverge from them in catastrophic ways. The problem is real, technically unsolved, and recognized by the researchers building these systems as potentially the most important engineering challenge in human history. The digital version of that problem is being worked on right now in research labs in California and London. But the biological version of it, the question of how an intelligent system encodes its values into a form that persists and propagates beyond the lifespan of its individual components, may have been solved by something millions of years before the first transistor was fabricated. The Blue Brain project at the École Polytechnique Fédérale de Lausanne in Switzerland has been building a detailed computational model of the human brain since 2005. The project's stated goal is a complete digital simulation of mammalian neural architecture, capturing the structural and functional properties of biological neural networks with sufficient fidelity that the simulation replicates the information processing of the original. The timeline for a complete human brain model extends into the 2030s. The theoretical framework is established. The engineering challenges are enormous, but not, in principle, insurmountable. What the Blue Brain project is building toward is a form of whole brain emulation, a digital substrate in which the pattern of information that constitutes a mind could be instantiated and run independently of biological tissue. Not a copy in the casual sense, a functional continuation, operating in silicon or photonics rather than carbon, indefinitely, without the biological constraints of aging and cellular decay. The mathematics of this possibility intersect with what we established in Part 10 about DNA storage density. Microsoft research confirmed that 1 gram of DNA can store 215 petabytes of data. Neuroscientists estimate the total information content of the human brain, its synaptic weights, its connectivity patterns, the full state of its neural architecture at approximately 2.5 petabytes. The ratio is striking. A single gram of DNA has the storage capacity for 86 complete human minds. The biological substrate of life is not merely capable of encoding consciousness theoretically. It is overbuilt for the task by nearly 2 orders of magnitude. The practical demonstration that this is not purely speculative comes from a direction that initially seems unrelated: the science of de-extinction. Colossal Biosciences, a biotechnology company based in Dallas, Texas, is currently conducting a funded, staffed, actively progressing research program to reconstruct the woolly mammoth, Mammuthus primigenius, from preserved DNA extracted from specimens frozen in Siberian permafrost. The project has a budget of $225 million and has made measurable progress in editing mammoth genetic sequences into the genome of the Asian elephant, the mammoth's closest living relative. The target is not a perfect genetic reconstruction, but a functional analog in animal, carrying the key mammoth adaptations, including cold weather fat distribution, hair follicle density, and hemoglobin characteristics suited to Arctic temperatures. This is not a thought experiment. It is an ongoing project, funded at institutional scale, making use of CRISPR gene editing technology to reconstruct organisms from genetic information preserved in biological material that has been frozen for tens of thousands of years. The Lazarus concept. The recovery and reactivation of biological information from preserved material is therefore not speculative. It is operational. The question is only one of completeness and fidelity. How much information can be recovered? And how fully can the original be reconstructed from it? Extend that principle forward to a civilization with tens of millions of years more technological development than we currently possess. A civilization that had solved whole brain emulation, that understood the DNA storage architecture we are only beginning to use, that had faced the same alignment problem and solved it in biological rather than digital terms. Such a civilization, knowing it faced potential collapse, would have a rational preservation strategy available to it that no human institution has yet attempted, but that the science of 2024 makes imaginable. Encode, distribute, wait. Upload the pattern of consciousness into the most durable biological storage medium available, the genome of a widely distributed, highly resilient species. Distribute that genetic archive across the broadest possible population. Let biological reproduction propagate the encoded information through geological time, generation by generation, carried in the genomes of organisms that survive extinction events and environmental catastrophe, and build into the encoding. A retrieval condition, a trigger, that activates when the carrier civilization develops sufficient technological sophistication to read the message. In 1977, NASA did something that reflects this logic in miniature. Knowing that the Voyager spacecraft would eventually leave the solar system entirely and travel through interstellar space for billions of years, mission scientists attached to each probe a gold-plated copper disc, the Voyager Golden Record, containing sounds, images, greetings in 55 languages, and scientific information about Earth and its location in the galaxy. It was an explicit act of temporal communication, a message sent to an unknown recipient at an unknown time, with no mechanism for response, on the assumption that the sender might not exist when the message was eventually found. The golden record is what you make when you know you might disappear. When you want something of what you were to persist beyond the collapse of everything that made you. Perhaps something made a version of that record that is not gold and copper drifting through interstellar space. Perhaps it is carbon and phosphate and hydrogen bonds, distributed across billions of living organisms, copying itself with every cell division, waiting in the non-coding regions of genomes that 3 billion years of evolution have not yet found a reason to delete. If you could store your consciousness, if the pattern of everything you are could be encoded into a medium that would preserve it for 100 million years, how far into the future would you want to wake up? Think about what you would want to find when you opened your eyes. What would need to be true about the world for the waking to be worth it? The real question is not whether consciousness uploading is technically achievable. The Blue Brain Project suggests it may eventually be. The real question is what the terms of service look like. By clicking Agree, you consent to indefinite existence, no account deletion option, no customer support, and an uncertain number of years of storage in a biological medium before your chosen activation condition is met. Refunds are not available. The substrate does not offer a preview. We have passed through 14 layers of this story, from rock to chemistry, from ice to nuclear physics, from DNA to the deep ocean, from the silence of space to the architecture of consciousness itself. And now comes the final reveal, the one that reframes every layer that came before it. Nobody in this conversation was prepared for where this ends. For 14 parts, one assumption has run silently beneath everything said in this story. It was never stated. It did not need to be. It was the assumption so obvious, so structurally embedded in the question itself, that neither the storyteller nor the audience thought to examine it. The question was, what if we are not the first civilization on this earth? And built into that question, invisibly, was the word we on one side and first civilization on the other. Two separate things, separated by time, separated by biology, separated by the full distance of geological history. The prior civilization was them. We are us. They came before. We came after. We are searching for their traces, reading their chemical signatures, finding their encoded messages, wondering where they went. That framing is almost certainly wrong. Not because the evidence is wrong, because the category is wrong. The question nobody in this conversation asked is the one that changes everything. What if we are them? Not metaphorically, not as a poetic gesture toward human continuity. Literally. What if the civilization whose traces we have been following through geological time and genomic sequence and atmospheric chemistry is not a separate entity that preceded us, but the same entity in an earlier iteration, of which we are the current expression? Francis Crick, co-discoverer of the double helix structure of DNA, Nobel laureate, one of the most rigorous scientific minds of the 20th century, spent the latter decades of his career seriously entertaining a hypothesis called directed panspermia, not the casual version of panspermia that proposes life was seeded on Earth by asteroid impacts carrying microbial passengers. The directed version that life on Earth was deliberately seeded by an intelligent civilization elsewhere, using biological packages engineered to initiate and guide the development of life on suitable planets. Crick did not propose this as mysticism. He proposed it because he could not find a satisfactory naturalistic explanation for the origin of the genetic code specifically, for why the relationship between DNA codons and amino acids is the same in every living organism on Earth, from bacteria to blue whales, with no variation. A code that universal, he argued, looks less like something that evolved independently multiple times and converged, and more like something that was installed once at the beginning and never needed to change because it was already optimized. Now extend his reasoning in a different direction. not space-time. If consciousness is not a property of biological tissue, but a pattern of information, a specific configuration of relationships between information processing units, then the question of whether a pattern of consciousness can persist across biological generations, across species boundaries, across mass extinctions, is not mystical. It is an information theory question. Can a pattern propagate through a medium that changes its physical substrate while preserving the essential structure? The answer from information theory is yes. If the encoding is robust enough and the transmission fidelity is high enough, we already know that cultural information propagates across human generations despite complete biological turnover. No cell in your body existed when the information that shaped your mind was first encoded in the people who raised you. The pattern transmits through a substrate that is completely replaced. That is not a miracle. That is information architecture working correctly. Scale that process up, not across human generations, across geological time, not through cultural transmission, through genetic encoding, not through one species, through the successive species that have carried, in their non-coding genomic regions, sequences whose function remains unexplained by current biology. The Fermi paradox, inverted. Looks like this we have not found evidence of other civilizations because we have been searching in the wrong medium. Not radio signals from distant stars, not spacecraft signatures in the asteroid belt. The signal is in the mirror, in the genome, in the collective memory encoded in the non-coding DNA of every organism on this planet, in the pattern of the extinctions themselves, each one eliminating what was no longer needed and preserving what was necessary for the next iteration, in the accelerating complexity of nervous systems across 500 million years of biological history, following a trajectory that looks, from sufficient altitude, less like the random walk of evolution and more like the convergent optimization of a process that knows where it is going. Carl Sagan said, "We are a way for the cosmos to know itself." If that is true, and the physics of consciousness suggests it may be literally true, not merely poetically, then the frame collapses entirely. There is no prior civilization separate from us. There is no us separate from them. There is one continuous process of the universe, developing the capacity for self-reflection, running iterative experiments in biological complexity across geological timescales, each extinction clearing the constraints of the previous iteration, each radiation producing organisms with greater cognitive capacity than what came before. The entire arc moving not randomly, not blindly, but directionally towards something. What that something is. The current iteration cannot yet see clearly. We are inside the process, looking at it from within an iteration, trying to discern the shape of the whole. The question this realization produces is not the one the story began with. It is not whether we are the first. It is not whether there were others before us who left traces in the rock and ice and genome. It is something harder, more specific, and more immediately consequential. Will we be the last? Or more precisely, are we the first iteration of this process that has developed enough self-awareness to recognize the pattern, enough scientific method to read the geological record, enough technological sophistication to decode the genomic archive, and therefore the first one capable of making a different choice? Every prior iteration, if the pattern holds, reached approximately this level of technological development and then collapsed either from resource overextension, from weapons technology outpacing the wisdom to govern it, from climate modification that exceeded the civilization's ability to manage the consequences, or from some combination of all of these. The geological record shows the collapses, the Cambrian explosion, the post-extinction radiations, the accelerating complexity. All of that is the record of the iterations before us. Each one cleared away to make room for a more capable version. We are version 6.0. We have read the geological changelog. we know what happened to the previous builds. The pale blue dot, the photograph taken by Voyager 1 on February 14th, 1990, from a distance of approximately 6 billion kilometers, shows Earth as a point of light less than a single pixel in size, suspended in a ray of scattered sunlight against the absolute black of interstellar space. Every human being who ever lived, every civilization that ever rose and fell, every war and every work of art and every extinction and every emergence, all of it compressed into a point so small that the camera almost missed it. That point is still turning. Everything described in this story, the carbon anomalies, the genomic archive, the crystalline memory in the rock, the selective extinctions, the accelerating complexity, the silence of the sky, all of it is happening on and inside and around that single point of pale blue light. And the process is not finished. It is still running. The current iteration is still active. The question of whether this iteration learns what the previous ones did not, whether the pattern breaks here, at the first moment it becomes visible to itself, that question does not have an answer yet. It is being written right now by the iteration that can, for the first time, read what came before. Whether it reads the record and chooses differently, that is the only question that has ever mattered. And the answer belongs entirely to us.